evening, y'all. You're going to get distinguished today. I didn't even spell it right. Distinguished today. Going to apply the Pythagorean theorem in three-dimensional figures today. Pretty distinguished. So, if you would do so, please make this the title of the next free page in your math notebook. And when you have done that, close it up, turn everything off, put everything away, turn on that brain, and just listen to what's time to write on we do. Excuse me. Okay. So before we get to 3D figures, let's review the kinds of 3D figures we've seen real fast. We've looked at prisms earlier in the year. Prisms have a base that is some shape. So in these cases, the base is a rectangle. In this case, the base is a triangle. And then all the sides connecting the bases are rectangles. So these are called rectangular prisms. These are called triangular prisms. Those are from earlier this year. We also looked at pyramids. So pyramids have one base, a triangular pyramid, and then their sides are triangles that come up to a point at the top. So they have one base. Prisms have two. You know, like this one's got a top square and a bottom square. This one's got a top triangle and a bottom triangle. That's the difference. When we get distinguished here, it's the ability to apply the Pythagorean theorem in situations with shapes that are challenging, to be frank. And so this is one. Find the length of diagonal D in this figure. So the diagonal D goes from here up to here. So you'll notice it doesn't even follow one side of the prism. It cuts kind of through the middle of it from one corner to the next. So we've dealt with diagonals earlier. And when we had a diagonal in a 2D kind of place, we made a right triangle out of it. And we used this side and the Pythagorean theorem to find this side. That's kind of what we're going to do today too, but it's harder. So if you imagine I try to make, the first hard part about this is visualizing where the right triangle even is. One side will usually follow the prism. So I'm going to, like this side I can trace down here. But what's tricky is, you'll notice, the other side doesn't follow the prism. It's not this side. That doesn't make a triangle. You know, and it's not this side either. It's not a side at all. It cuts, you know, to get the base of that right triangle, we've got to cut through the bottom like that to make our right triangle to find D, and we make our right angle with this side, which we know, but also this side we don't know. I don't know what the distance is from corner to corner like that. It's not in there. So that makes this pretty tough to make my right triangle. There's my right angle. That's why I was trying to do that. So I've got a missing side, which means I've got to make another right triangle to find this first. You'll notice I can make a second right triangle with that being the hypotenuse if I use this side of the figure and this side of the figure. It doesn't look like a right angle because of how it's drawn, but remember this is the corner of the prism, so it is a corner. So now I can use the Pythagorean theorem to find this side. That's the diagonal of this triangle made by the bottom. So if that's true, a squared plus b squared will equal c squared for that triangle in yellow. One leg is 10, one leg is 6, and I don't know the hypotenuse. So that's 100 plus 36 equals c squared. 136 equals c squared. I don't know the square root of 136 offhand. It's going to be between 11 and 12. Right there, 11, I'll round it to approximately 11.66, let's say. So that helped me find this one. Now I can use that side to find this side that I don't have. So maybe retrace in red here, let's say. So I found the hypotenuse of that first triangle. Now I've got leg, leg, and I can find this hypotenuse. So tricky, got to apply the theorem twice to find that diagonal, very tricky. So now in my new one, leg squared, which is that, plus leg squared equals whatever that diagonal is squared. I'm going to call it D actually, even though we usually write C in the theorem. This squared is going to be this, because I just did that down there. I think it's easier if you think of it that way. Think, oh, well, I did a square root to get from here to here, so if I square that, I'm going to get that. Because since I rounded it, if I put the rounded value in my calculator, it's going to not be quite 136. It's going to be super close, but since I rounded it, it won't be exact. Not a huge deal if you use this number rather than excuse me, than 136. But since you know it, I did round that. That's the square root, so squaring it's just going the other way. This is more precise. 15 squared is 225. Add those together. 361 is D squared, so D itself is a 19. And that is how you do it. So it usually takes applying the theorem twice. Once to find this leg, then a second time to find the diagonal. Open your notebook. Let's try one together. Go ahead and pause here and give this a draw. A very similar problem. And we'll give it a go. All right, so the first thing to notice is where the diagonal starts and ends. So it goes from that corner to that corner. Imagining seeing stuff in 3D when it's really drawn in 2D is kind of tough. So that diagonal cuts through the middle of the figure. So to find a diagonal, we've done that before in a different situation. So to find a diagonal, what you'll end up doing is making a right triangle, right? We kind of like add two legs to it, and that's how we do it. So to do that here, I'll start in yellow. To make a right triangle where that's the hypotenuse, I would drop down to the bottom of the prism. And then, and that's nice because I know that distance. But unfortunately, to get back there and make a right triangle, I can't follow this, won't get there, and I can't follow this, won't get there. I've got to make another diagonal through there. Now, important to notice, because this is in 3D, it doesn't look like I drew a right triangle. It doesn't look right. But this is a right angle because we came straight down and then followed straight across the bottom. So it doesn't, it's a kind of an optical illusion because of how it's drawn, but we do end up with a right angle there. And since we have that right angle there, the first thing to do is to find this. Find this diagonal first. So that one we do have the other two legs. We've got this one and this one. And I can use that leg and that leg to find that hypotenuse. Again, doesn't look like a right angle because we're in 3D, so kind of weird. You have to kind of make your eyes see that as a right angle, but we can. So since that's the case, a squared plus b squared equals c squared. So 3 squared plus 4 squared equals c squared. This is a Pythagorean triple. 3 and 4, you'll get used to it. This is a very common right triangle because that's 9, that's 16, and those make 25. So a 3, 4, 5 right triangle is super common. If the legs are 3 and 4, the hypotenuse is 5. That's just a Pythagorean triple. You'll get used to. We've seen it a lot. So now I've got that. And once we've found that, second, I'm going to have some space here. Second, you can find the diagonal. Find the main diagonal, we'll call it. I had to know that 5 first, because now I have leg, I can find this hypotenuse, but it took some time. So that will be 5 squared plus 12 squared equals c squared. This is another famous Pythagorean triple. 5, 12, this will end up being 13. 3, 4, 5 is a famous right triangle. 5, 12, 13 is too, if you're not used to that yet. 25 plus 144 equals c squared. Those make 169. And the square root of that is 13. Boom. And that's it. So usually to find those, you're just going to have to apply the Pythagorean theorem twice. Once to find the kind of the base of the triangle you make with it, and then once to find the hypotenuse itself. Very distinguished, y'all. I hope it made sense to you. I tried to be as clear as I could. If I wasn't, give it another watch. I think this will help a lot. It's only 10 minutes. You can spare it. And if you do, you'll come to class tomorrow super confident. See you then.